started off having gone through basically looking at all of the different kinds of equilibrium coefficients that we are going to use. Now, let's look at an example of this, because essentially we're going to look here at equilibrium, and we're going to examine what happens if we change it or we do certain things to it. Now, I want to always start off, number one, with balanced chemical equation. All right, remember we note the phases of our reactants and our products, just so that we're aware of what we're mixing here. We're going to have a look here, and we're going to say in this one that we put 0.4 moles, okay, so we place 0.4 moles of PCl5 into a vessel of, and I think I used 10 liters, and allow to reach equilibrium. Okay. At equilibrium, I'm not going to change equilibrium, we find that we have 0.25 moles of Cl2 gas. Okay, that's also a gas into a vessel of 10, allowed to react to reach equilibrium. At the equilibrium, we have 0.25 moles of Cl2 gas. And the question they're asking is calculate the Kc, the equilibrium coefficient. So according to this equation, and they will give you the equation in most cases, the equation is P, let me just move it slightly over, because we're going to be doing a table, PCl5 gas plus Cl2 gas, eek, goes to, my bad, that goes like this to equilibrium, goes to PCl3 gas plus Cl2 gas. Okay, now when we're looking at this, what do we know? Well, first of all, they've given us the volume, and they've told us certain things. Now, in your books, some people use, there's two different ways, okay? I prefer one, others prefer it, but it's the same thing. It's called the ICE table. The ICE table is initial, change, equilibrium. I'm just going to change the change bit to use and produce. I'll show you why. It's the same thing exactly. Okay? So, firstly, we're going to write the chemical step 1, balance, and then step 2, oops, come on, move you up a bit. Step 2, we're going to put in 1 goes to 1 plus 1. Right? Now I put my double line down here because I'm going to work with this, and I draw a line across there, which gives me now I can actually start. I say here, I use the word initial. Initial. That is our at the start. All right. Change, I use here use and produce. And equilibrium over here. Equilibrium, below I write in volume and concentration. Because I know I have to reach concentrations. That's important. So get that table down, and then I'm going to go. So initial, now over here, this piece here is the change, which is the IC, and here is my equilibrium is the E, the ICE chart, okay? I've just put, I just like it this way. I've seen it in previous textbooks, and I don't know, each to their own. It just makes more sense when I teach it to students here. They seem to like the use and produce because it kind of makes sense, okay? Change becomes, you have to do a plus or a minus, all right? Obviously minus if you use, plus if you make. Now, let's have a look. Okay, so we've got the table. The next step, number 3, okay, let me just move up here slightly. Step 3 is fill in. Fill in given. All right. Okay, now let's see. On the given side, what did we have? We had over here at equilibrium, all right, we had 0.25 moles of chlorine gas. 0.25 moles. Right? Volume I'm putting in was 10 liters, which is equal to 10 decimeters cubed. Okay? Now, they said that we started with 0.4 moles of that. Now, in the table above there, you can use moles. Okay? We're going to use moles in here. So I say at the start, did I have any PCl3? No, obviously not. Go back to the graphs. We started, all right? We could have had some, but in this case we didn't because we said we put in the PCl5 and allowed it to decompose to equilibrium. So we had at the start, we had no product. Because remember, reactant and products. There we go. Activated complex in the middle, but we don't need that. We don't need delta H in this one either. So what do I say? I say, okay, initial change equilibrium. So I've got that. Now my concentration, straight away, I can fill in the concentration. All right? So we made product. Right? So I'm just going to draw a line just a second here. Right? I'm just going to stay working above that line just for the moment. Let's fill in the table. Okay, the next step is to say, right, therefore, did we produce or use up PCl5? All right, we must have used it because we produced. So we used PCl5. Therefore, all right, we've got that there, we don't know, and we didn't produce any, so we can cross it off. Chlorine gas, we produced 0.25. There it is. We didn't use any, and we didn't use any of that either because we didn't have any. Just remember, the PCl5 was put in, then it allowed to decompose to PCl3 and Cl2. So we used reactant, made product. This is the change. Okay. So if I use it on change, would be for use, would be minus, and produce would be a plus sign. By keeping them in the table like this, I don't need to do that. I can just, it's obvious. So 0.25. So now my question is, okay, now look, we've got these spaces are blank here. Right? And this is also blank. Right. Now, if I had 0.25 moles of Cl2 gas at equilibrium, how many moles of PCl3 must I have? I must have the same because it reacts in the ratio 1:1. I must have the same number of moles. Therefore, if I've got 0.25 of this, I must have 0.25 of that. Okay, makes sense? Let me just change it to blue because it's, I think, a bit nicer to read. Okay, I must have 0.25 moles of that because they react 1:1. There it is. So if I've got that, I must have that. Therefore, I can fill in that's 0.25. All right? Therefore, now going through the table here, if I use 0.25, I've had 0.25, how much did I use? I also used 0.25 because once again, it's 1:1. Every 1 mole of PCl5 gives me 1 and 1. You can see how critical that is now. So therefore, how much at equilibrium is going to be 0.4 minus 0.25, which is 0.15. Right? 0.15, like so. Shall we go through it again? And then we'll get... So what do? We drew the table. Initial, or start. Use produce, which is change. And equilibrium. Underneath, I put in volume and concentration, just to remind me that I still have to do that section of work. Then I put in what I know. I've been told that I had 0.5 moles at the beginning. Sorry, 0.4. 10 liters is 10 decimeters cubed always. I had 0.25 of that. I know I had no product at the beginning, okay, and I can immediately say, what did I do? I produced reactant. Therefore, I need to fill in these two, and I can immediately cross out I did not produce any reactant because it went in the forward direction. Could have gone backwards, but it went in the forward direction. Then when I put in those, I now say, right, starting with the moles that I've got here, I said, okay, if I've got 0.25, therefore I must have produced 0.25. Is that not so? And I must have similarly had 0.25 of PCl3 because it must react 1:1 ratio. It's all coming back to that ratio. That is the critical portion of this part of the work. Then we go back and we go through the wall over here. I called it the mole hole in previous things. I can go through because I know moles. Therefore, if I produced 0.25 of each, I must have used 0.25. Therefore, in my container, I've got 0.15 moles left, 0.4 minus 0.25, and therefore my concentration at equilibrium is going to be 0.15 over 10. And over here, 0.25 over 10, okay? And here, 0.25 over 10. Okay. Let's go and calculate what Kc is now. All right, over here, therefore Kc, always write down the mass action expression. PCl3 times Cl2 over my PCl5, which is that one, and we can work it out. That's 0.025, 0.015, whoops, 0.015, 0.015 moles per cubic decimeter, 0.025 moles per cubic decimeter, and 0.25, that's a 2 there, 0.025, Kevin, moles per decimeter. So then I say the Kc must be 0.025 times 0.025 multiplied by or divided by 0.015, and that comes out to be, I think, 0.4 something. Let's just check my arithmetic over there. Let me just check it before I get shouted at and said, well, that's wrong. It's 0.025 times 0.025 is equal to that, divided by 0.015 is equal to 1 over 0.417. 0.417, all right? Or 0.42 if you wanted, depending on where they want you to round it, 0.42 at whatever the temperature was that they told us. Okay? So let's have a look at another question now. Okay, this one's going to end up using the ice table as well. This question here says to us, all right, the following is given at 448. So this is example 2. The following is given at 448 degrees centigrade. These temperatures are quite high. We've got H2 gas plus I2 gas going to 2HI gas. Step 1, okay? And they tell us that at equilibrium, blah, blah, blah. Step 1, always write down what you've got. 1 plus 1 goes to 2. That's our mole ratio, isn't it? Then they say at equilibrium, the concentration of H2 is equal to 0.46 moles per cubic decimeter. The concentration of I2 is equal to 0.39 moles per decimeter cubed. And the concentration of HI is equal to 3 moles per decimeter cubed. All right? And they say calculate Kc. Okay? Kc is equal to concentration of HI product squared divided by the concentration of H2 multiplied by the concentration of I2. So therefore they've given me that is going to be 3 squared over 0.46 times 0.39. And when I calculate that, I get 50,17. Okay? And no, there's no units. All I've done is I've put those into the expression of mass action, which is a very simple thing to do. The next part of this is they say, let's go and take this one up. Correct. Do the next one. Then they say to us, okay, using the same reaction, so this is part 3. Using the same reaction, okay, as above, at the same temperature. Why do I say that? Because if the temperature changes, Kc changes. So I'm using the same values. So my Kc is going to be the same at the same temperature, okay, and at equilibrium. Okay, the concentration of H2 is equal to the concentration of I2 is equal to 0.6. Okay, calculate the equilibrium concentration of HI. Right? Always we start off with balanced reaction. We've done it before. Let's rewrite it. H2 gas plus I2 gas going to equilibrium 2HI. Expression of mass action. We'll always write it down. HI squared over H2 and I2. All right? The H2 and the I2 must always be equal. Okay? Well, the ratio of forming 1 to 1 to 2 must be always equal, must always be preserved, 1 to 1 to 2. It's not necessary the concentration of H2 and I2 at equilibrium must be the same. The concentration of the products that you make must be in the mole ratio. So we've got here, so now we say Kc, we know that Kc was 50,17. I can use it. So therefore I can say the concentration of HI squared must be equal to the concentration of 0.6, 0.6. They could have told us moles and then, for example, given us a volume. Always look and make sure that you're calculating concentrations. Therefore, the concentration of HI is squared, okay, is going to be equal to the 50,17 multiplied by 0.6 by 0.6. I've just multiplied that way, and to the power of a half, I took the square root, is 4.25 moles per cubic decimeter. Right. That's part 3 of that. Part 4 of the same equation. Part 4. They say the equilibrium constant Kc is that for the following at this. Okay? So Kc equals 50,17 at T equals 448 for the following: H2 gas plus I2 gas going to 2HI gas. All right? Now, this is a different problem. So, I hope you're writing these down as we go. They tell us now the following. They say 1 mole of H2, 1 mole of H2 gas is mixed with 1 mole of I2 gas. Okay? In a 0.5 decimeter cubed container. All right? And is allowed to come to equilibrium. And is allowed to come to equilibrium. All right? Now, there's a whole load of questions that we can ask about this. But what they essentially want to know is they want us to analyze the problem. Okay? Let us thus, step 1, we've given us the initial moles, haven't they? They now want us to calculate whatever. Let's see. Let's put the table down first. So first of all, I'm going to say here, H2 gas plus I2 gas going to 2HI gas. Now I'm going to put in, there's my double line coming, and I put 1 plus 1 goes to 2. Okay? I was going to confuse things, but I'm not. There's my line. Now I put in here initial, which is the start, what I've got. I put in here change. If you like my method, you can use it. Start, use, produce. And over here is our equilibrium. And at the bottom, we put in volume and concentration. And I said, okay, put in what we're given. Well, we are told that we start with 1 mole and 1 mole of those. Okay? Now, therefore, we are making product. We are going that way. All right? I think every single one of these I've seen is making product. Okay, the next step is to ask ourselves, therefore, did I use up H2? This is my reactants. This is my products. Did I use up reactants? Yes. So I used up these. I didn't produce. And I didn't use this. I produced. Therefore, at equilibrium, I draw the line. Now I say to myself, all right, what have they told me here? What have they told me over here? All right. They have told us that what I've got here is I've got a equilibrium condition. And they have told us that Kc is given. Very often when Kc is given, that's a hint that you're going to have to use an X. Because look, they didn't tell us how much of the rest was there. We are missing a lot of information. Therefore, we say, right, I am going to say X there. Therefore, call one of them X. The next step is to say, X, how many, if I used X moles of hydrogen, how many moles of I2, iodine gas must I use? Equally X moles. It must be, because this must react in 1:1 ratio. For every mole of H2, I must use one of those. It could have been 1:2, which means x 2x, or x half x. Okay? You'll see it now. Now continue through the table. If I use 2 of those, how many HIs must I have? 2x. Why? Because this reacts in the ratio 1:2. For every mole there, I must use 2 mole. I must get 2 moles of HI. The next step is to say thus at equilibrium, I have got 1 minus x moles and 1 minus x moles. And over here, I have got 2x. Have I not? Therefore, the volume was given as 0.5. Let me go back. All we're doing is filling in the table here. Therefore, the concentration is 1 minus x over 0.5. 1 minus x over 0.5 moles over volume, and over here is 2x over 0.5. So far, so good. Just to recap it, I put my table and I put in what I know, and you can see I do not know enough to fill in. I'm not given information, so I let one of the reactants be x. And I then use the mole ratio to say, if I've got x moles of one of the reactants, how many moles of the other reactant must react? It reacts in the mole ratio between them. Then I go through the table to the product, and I say, if so much is, how much product must I get? We're going to do it with ammonia later, where we've got different mole ratios on either sides. The final step is to always write out the expression of mass action. Therefore, Kc, I often say that's T is equal to 448 degrees centigrade. That's not necessary. I just do it for my own thing to say that I've got the temperature. And then I say, okie dokie, therefore, my expression of mass action is going to be Kc is going to be equal to concentration of Hi squared divided by concentration of H2 times concentration of not N2, I'm thinking already of ammonia, of I2, right? And I fill it in. Concentration of Hi is 2x all squared. Concentration of these guys, 2x over 0.5. Okay, sorry guys, be careful of that, okay? I did the 2x. Always go to the concentrations when you fill in. Over 1 minus x over 0.5 times 1 minus x over 0.5. And this must be equal to 50,17. Why? Because that was given. It was given to us. And unfortunately, this comes out to be quite a nasty quadratic. I am going to skip the entire thing of solving. What you will do, just so that you, from a maths point of view, you would multiply out, you would then invert and cancel out, and you end up with something like this. Black, let me just move it up a bit, and I'll put where we end up is going to be 50.17 times 1 minus x, because the 0.25s cancel. Okay. Because it's 0.5 squared, and that 0.5 times 0.5 is the same, it's going to cancel out, is equal to 4x squared. Basically, you're going to end up with a quadratic of 46,17x squared minus 100,34x plus 50.17 equals 0. And you're going to solve that with a calculator. x1, 1.34. x2 is equal to 0.78. And what's the answer? It cannot be this one, because we start with 1 mole. Therefore, not a solution, not applicable. Therefore, it's 0.78. Therefore, the number of moles used, is equal to 0.78. Now I can go back to my equilibrium table. I'm going to put it out here now. Okay, H2I2 and 2HI. Right? This, all I'm doing is copying what I had before. Okay, I said start used, started with 1. Used is 1 minus 0.78, correct? Okay, over here I was 1 minus 0.78. Therefore, used, okay, therefore, produced is going to be 2 times 0.78. This is equal to 1.56. That is going to be, the used portion is equal to, let me move produced down over here a little bit. Okay, produced is this guy. Used is 1 minus 0.78 is 0.22. And over here, 0.22. Therefore, concentration, I didn't produce any, I didn't use any. So therefore, concentration is going to be 0.22 over 0.5, 0.22 over 0.5, and this is going to be 1.56 over 0.5. Let's go back to Kc. Therefore, Kc is going to be 1.56 over 0.5 squared, right, divided by 0.22 over 0.5 and 0.22 over 0.5, and that gives me 50,2, which is close enough. Okay. There we have done a full one. All I can suggest to you is work through that one very carefully. Go through it step by step. Once you've got the hang of that, it doesn't matter if these mole ratios change. Show you one in the next section. If the mole ratio over here, let me just get to it. If the mole ratio, now I'm going to use green. If the mole ratio there was 1 to 2 to 3, which we're going to see, you just apply the mole ratio like a normal stoichiometry calculation. In the next one, I'm going to look at a Haber process, very similar. We're going to look at a Haber process, and then we're going to look at some acids as well, calculating the concentration of acids. The next one's going to be more examples. All I can say is please go through this one very carefully that we've just done from the beginning to here. Once you understand it, you will see it's repetitive, but you always will be doing exactly the same thing. It's not going to change. Cheers. Thanks for watching. Appreciate it. I'll come back and we'll do some more examples. Cheers for now. Bye.